Today we will discuss uh, fats and oils, edible fats and oils, their basic chemistry, as well as some idea on processing. Now, to start the discussion, we must know what is the basic difference between the edible fats and oils and the fats and oils of biology, which is grossly known as biological lipid. The difference between biological lipid and edible fats and oils is that the composition is quite different in case of edible fats and oils, but in case of biological lipids, grossly all hydrophobic substances which are present within the cell are known as lipids. It is not their property, biological lipids, their property is not limited to their hydrophobic character, but they do a number of functions within the cell. But to recognize them as lipid, this is a simple such characterization of lipid, that they are hydrophobic in nature. The lipids of biology, which include a large number of substances starting from free fatty acid and cholesterol, and also a large number of phospholipid molecules along with triglycerides. In case of plant lipids, also waxes, lot of substances are there. But edible fats and oils, which are only the triglycerides, that means the fats and oils we consume, these are typically triglyceride molecules, but when we extract them from the natural sources, for example plant seeds, various other plant body parts, the byproducts, different food processing byproducts, particularly the cereal grains, they are milling, which generate bran, germ, etc., rice bran, corn germ. They also are subjected to extraction, and the vegetable oils extracted we get in case of solvent extraction, which is a very rigorous technique. The extensive solubilization of the contents of the raw material which come into the solvent fraction, they contain a large number of compounds and various types of lipids which are soluble in organic solvents like hexane, etc. Now these substances, once collected after extraction for the production of edible fats or oil, they are subjected to refining. So refining is needed to separate the other undesirable components of the lipid from the raw material, extracted oil, and to isolate the triglyceride as the edible part. So triglycerides these are the edible. Edible lipids. We cannot consider any other type of lipid substances as edible lipid. However, every time we cannot separate them from the food material where lipid is present as cellular material during processing of food and as a component of food. When we use these lipids, various other substances which are not triglycerides, but they also remain within the food. But the desired thing is that when those non-triglyceride fractions of lipids are included within the food material, they will be in limited quantity, and in case of preparation of certain food materials, certain processing, we need these phospholipids and other lipids as emulsifiers. In those cases also they are present in limited quantity, but we cannot say that the lipids present in food or the lipids which we consume is grossly these phospholipids and everything. We never consume phospholipid, but our desired edible lipid, those are triglyceride molecules. So let us start with the chemistry of triglyceride molecules. A triglyceride, as the name suggests, it is the glycerol ester of fatty acid. This is the glycerol ester of fatty acid. R1, R2, R3 are the hydrocarbon part of the fatty acid. Here it is quite evident that this is the glycerol part, this is the glycerol part, and the remaining, they are the fatty acid esterified with these 3 hydroxyl groups of glycerol. This is also known as this bond is known as acyl ester bond. It is quite interesting in the structure of triglyceride that glycerol itself has 3 free hydroxyl groups. 2 of them are primary alcoholic group. If we can write the glycerol separately, we can see this is glycerol, this is glycerol, this is one primary hydroxyl group, another primary hydroxyl group, and this one is a secondary hydroxyl group. This is primary CH2OH, primary, this is also primary, this is secondary hydroxyl. Now this glycerol, when it forms the triglyceride molecule, it forms bond with the fatty acid. Fatty acids actually, though in the chemistry of monocarboxylic acid, everything are grouped within the fatty acid class, but the lipids of our edible food material, the triglycerides present in those food material, they contain mostly the fatty acids of medium to large and very large chain containing a large number of carbon atoms. So fatty acids themselves determine the property of the edible lipid. Fatty acids themselves determine the property of the edible lipid. Glycerol has no role in determining the property of the triglyceride. Glycerol only bind these fatty acid to produce the triglyceride. The molecular weight, for example, the molecular weight is governed by the fatty acids present in the glycerol molecule. Mostly the edible fats and oils, the triglycerides, they have the molecular weight ranging between 500 to 1000. And on an average, most of our edible oils like soybean oil, palm oil, those oil contain 800 to 880. They have the molecular weight like this. Now fatty acids let us see what are these fatty acids. The simplest such fatty acid, if we say, is formic acid. Formic acid is not at all present in edible fats and oils. Next comes the acetic acid, monocarboxylic acid, straight chain aliphatic monocarboxylic acid. Now acetic acid, in case of a few plant material, plant oil, acetic acids are sometimes present not due to their common constituents they produce, but due to some secondary metabolic action. Some metabolic action, this acetic acid is produced, and this acetic acid may be present in traces quantity. In various microbial oil also may be present, but acetic acid is not a common fatty acid. The next fatty acid which comes is propionic acid. Propionic acid. Propionic acid is also not present because it is odd carbon fatty acid. The natural fatty acids in the triglyceride resin are mostly even carbon fatty acid, and only those oils which are generated within the biological cell due to this propionyl CoA pathway, they produce this odd carbon fatty acid. In animal fats, in milk fat, in some different types of fats, those odd carbon fatty acids are present, but usually our edible oils and fats do not contain these odd carbon fatty acid. They are by and large even carbon fatty acid. Now after this propionic acid, next acid is butyric acid. This butyric acid is found in milk fat, and butyric acid has a typical flavor. Butyric acid. Butyric acid. Carbon, according to IUC system, carbon 2, carbon 4. 4 carbon fatty acid. This is a monocarboxylic acid. This is a monocarboxylic acid. Monocarboxylic. Next is saturated. We do not find any double bond in this fatty acid between carbon-carbon linkage. There is no double bond. Saturated fatty acid, straight chain. Straight chain, there is no branching. These are a few properties of the fatty acids present in edible fats and oils. If we say, if it is not monocarboxylic, it is dicarboxylic or any other more than one carboxyl group containing fatty acid. No, in edible fats and oils, those fatty acids cannot be present. That means only one carboxylic acid should be present in fatty acid which are derived from the edible triglycerides. Next comes whether saturated or unsaturated. Yes, saturated fatty acid is present as well as unsaturated fatty acid also present. But unsaturation of edible oils, the fatty acids of edible oils is limited to a double bond. Never a triple bond is present. That is also, if a triple bond is present in a hydrocarbon, it is also called unsaturated hydrocarbon. But in fatty acids of edible fats and oils, no such triple bond should be present. That what we select as edible oil, those compounds should never be present. Next comes the whether it is straight chain or branch chain. Chain branching actually is not present in edible fats and oils. There is always a straight chain compound. Branching is not present. Another thing is that no substituents should be present in this straight chain compound. If we say no, I found a fatty acid in the food like this, it is not possible. Hydroxyl group, chloride group, substituents, those substituents should not be present. Epoxy acid is not edible fatty acid. Epoxy group is present. CH2. Cyclopropene fatty acid, cyclopropene structure should not be present in edible fatty acid. Cyclopropene structure should not be present. Like if it is a hydrocarbon part of fatty acid, in one end there will be a carboxylic group since it is a fatty acid, in other end there will be the remaining part of the hydrocarbon of this. So this fatty acid if present in the oil, that oil is also not edible oil. So the common characteristics of edible oil fatty acid is they are straight chain, aliphatic. It is not alicyclic or anything. Straight chain, aliphatic, monocarboxylic fatty acid with medium to very long chain. So it may start with 4 carbon like butyric acid, but mostly the vegetable oil they contain 16 carbon fatty acid, and maybe this fatty acid, this 16 to 18 carbon fatty acids are most common. Lauric acid also present in abundance in some vegetable oil, for example coconut oil, etc. Let us see then the other biological lipids. What are the other biological lipids? Biological lipids, we can say triglyceride, monoacyl glycerol, diacyl glycerol, Number 4, phospholipids, very important lipid. Phospholipids. Number 5, waxes. Number 6, sterols, very important group of compounds having several functional roles. Sterols. There may be also hydrocarbons. Even a number of pigments which give rise to the color of the plant material. Those pigments are also included in this lipid class. Different pigments like chlorophylls, carotenoids, these pigments are present even in the oil, and they are also classed as biological lipids. A large number of compounds therefore are present. And last but not the least, the free fatty acid, because during metabolic process in vivo, the free fatty acids are continuously generated and those free fatty acids are utilized to produce other compounds, like one of them being triglycerides. So free fatty acids are also included. One may find these free fatty acid fractions once these oils, vegetable oils, are extracted by solvent extraction. I am again and again telling solvent extraction. There are several other extraction procedures also, for example pressing, etc. But pressing, the mechanical pressing or hydraulic pressing does not produce this other undesirable part to a great extent, because those are milder action. On the other hand, solvent extraction, they extract whatever lipid components are present within the solution phase, and then you require a refining operation to separate the triglyceride. That is why solvent extraction, they generate extracted crude oil with large number of these undesired components within the edible oils and fats, of which the triglyceride of course predominates. Otherwise this process would not be so it would be expensive. So it is economical that once the extracted material contains very high percentage of triglyceride, which is the desired part, then refining removes the minor quantities and separates the triglyceride to an extent of 98 to 99%. So the phospholipids, among them this monoacylglycerol and diacylglycerol. Glycerol, when esterified with fatty acid, 3 molecules of fatty acid, it is a triacylglycerol. But monoacylglycerol means only one fatty acid is esterified, the remaining 2 hydroxyl groups of the glycerol are free. So monoacyl and also diacylglycerol having 2 such esterified fatty acid, but one hydroxyl group, it is free. Either it is a secondary hydroxyl group of the glycerol, or any of the 2 primary alcoholic group may be free to give rise these 2 types of products. Now this monoacylglycerol and diacylglycerol, they to some extent can be grouped with this phospholipid because they have the polar lipid property. They are used as emulsifier in various food materials. This monoacylglycerol, diacylglycerol. Why? Because this free hydroxyl group on the glycerol carbon. This is the glycerol. Suppose this is a fatty acid. R2, and this primary alcoholic group, suppose it is free, so it is a diacylglycerol. Now carboxylic group in a monocarboxylic aliphatic acid may be having the polar characteristic. That polarity also varies depending upon the size of the molecule and the plus I effect of the alkyl group. But besides that carboxylic group, the remaining part of the molecule is completely hydrophobic in nature. It has no polarity in any part of this hydrocarbon molecule. Whereas, since this carboxylic group is esterified with the hydroxyl of the glycerol, there is no polarity. This part does not give rise polarity. it is completely neutral. So it is highly hydrophobic in nature, these two carbon atoms. But this part, hydroxyl group, can form hydrogen bond with water. That is why they behave like emulsifier in water. They having emulsifying property, amphipathic property. That means partially this molecule bind with the water molecule, and the remaining part of the molecule they tend towards the hydrophobic material, hydrophobic solvent if present, then they will remain away from the water molecule. So monoacyl glycerol, diacyl glycerol, they are hydrophobic they are emulsifier in nature, and also it is mentioning that they are very difficult to separate from the triglyceride fraction. They remain at least by 1 to 2% even after complete refining operation. When refining, either chemical refining or physical refining is completed, they remain by 1 to 2%. That part is very difficult to remove, and if you try to do that, your plant will suffer a huge yield loss. So this monoacyl glycerol and diacyl glycerol, phospholipid also, they are known as polar lipids, while triglycerides are neutral lipids. Phospholipids are polar lipids. A phospholipid CH R2. I am writing this R1 R2 to show that these fatty acids are different. These fatty acids may be similar fatty acids, but to distinguish them from each other, I am writing R1 and R2 like this. The number of, in terms of number of carbon atoms, and also double bond or single bond, they are different, the remaining part of the fatty acid molecule. Now the third carbon of glycerol, they form a ester, phosphate ester X. This is any other part. This may be an amine, it may be a sugar, etc. But phosphate is definitely present in phospholipid. This part is common in all phospholipid molecules. Now see what happens. These two carbon atoms, they are actually esterified, and this part of the phospholipid molecule has no polarity, because after esterification of this carboxylic group, the molecule goes as neutral molecule. They are no longer polar in nature. But this part, actually, this phosphate having this residual polarity, this polarity is there, and if this part is polar, this part is non-polar. So that is why they are emulsifying in nature. This part can bind with the water molecule, while these two tails, if we call it is a polar head, it is a polar head, and these are the non-polar tails. Non-polar tails, polar head, non-polar tails. That is why they are emulsifying in nature. The sterols are important group of compounds in the lipid. The sterols, plant sterols, actually these are helpful. When we consume plant sterol in our food, they can replace cholesterol. Plant sterols are phytosterols, while animal sterols are cholesterol. Cholesterol create problem in our body, blockade of artery, etc. Those problems are there. Now cholesterol can be replaced by phytosterol. However, phytosterol is not digested in the body and those are excreted. That is the advantage. And the sterols of plant, they are known as phytosterol. Whatever may be the origin of sterol, they have a common backbone which is known as cyclopentano parhydrophenanthrin ring structure. Cyclopentano parhydrophenanthrin ring structure. This is the cyclopentano. Why parhydro? There is a double bond and this hydrogen is removed, and here there is a hydroxyl group, and here there is a hydrocarbon part. It is CH2 hydrocarbon part. Here there are methyl groups. This symbol means there will be a methyl group in organic chemistry. If this is like this, there are two methyl groups, and there is CH2 like this. This is cyclopentano parhydrophenanthrin ring. Cyclopentano parhydrophenanthrin. Now these sterol compounds are also present. A very big molecule, but while we remove them in the refining operation by heat treatment at a very high temperature, this is decomposed and it produces smaller fragments, smaller molecules which are volatilized, distilled off from the oil by a process called deodorization process. During deodorization process, these sterols are also removed. Sterol is those group of compound. Let us go back again into the fatty acid, because fatty acids are very important compounds in edible fats and oils. In terms of fatty acid, the oils are named. For example, soybean oil, very common oil. Soybean oil, triglyceride. Soybean oil means we are only concerned about the triglyceride because those are edible oils. Soybean oil triglyceride, we are writing is it tag. That means it is also called triacylglycerol. Triacylglycerol. Similarly, monoacylglycerol is known as MAG. Diacylglycerol is known as DAG. Now, soybean oil triglyceride contains, if you hydrolyze these triglyceride molecules, you will find a large number of different fatty acids, of which linoleic acid will predominate. This linoleic acid is 18:2 fatty acid. 18:2 means first number is for number of carbon atoms. And the second number is double bonds. This is not, this is2 sign is not due to that actual meaning of this ratio or proportion, but 18:2, that means 18 carbon fatty acids starting from the carboxylic end. If we consider this carboxylic carbon is carbon 1, there will be 18 such carbon atoms. At one end there will be a methyl group on the rear side of this carboxylic group. In between there will be carbon and hydrogen. no oxygen, epoxy, any other derivatives, any other branching, but two double bonds will be there. More precisely, these two double bonds will be at 9 and 12 position in case of linoleic acid. That is why this linoleic acid is represented as delta 9, 12 fatty acid. If we say delta 9, 12 fatty acid, and if we say within bracket 18:2, it is the linoleic acid and no other fatty acid. That means if this carbon is one carbon, then 2, 3, 4, 5, 6, 7, 8, 9. Here there will be a carbon and there will be the first double bond. So here another carbon, it will be carbon number 10. Then comes 11, 12. There will be another double bond between 12 and 13. Then comes 14, 15, 16, 17, and this methyl is number 18. So in this way we name them. Soybean oil, since linoleic acid is abundant, about 42%, 42.8% linoleic acid of the total 100% fatty acid extracted after hydrolysis of soybean oil triglyceride. Linoleic acid will be this percentage. The remaining fatty acids are oleic acid, palmitic acid, many other fatty acids. The triglycerides of edible fats and oils are a mixture of triglycerides containing a large number of different fatty acids, both saturated and unsaturated. Usually, you will not find a triglyceride, natural triglyceride, having only unsaturated fatty acid present in the triglyceride. You will not find a triglyceride, natural triglyceride extracted from any source, which is containing only saturated fatty acid. So only saturated, only unsaturated, this type, there will be a mixture of saturated and unsaturated fatty acid. However, the vegetable fatty material, vegetable oils extracted from plant materials, they contain unsaturated fatty acid in abundance, and that is why their melting point is such that at room temperature they remain as liquid. So higher the unsaturation within the fatty acid, the lower will be the melting point of that triglyceride. So as I have said earlier in the beginning of this discussion, that fatty acids determine or dictate the physical and chemical property of the triglyceride or edible fats and oils. It is quite true that once higher unsaturation, higher degree of unsaturation, that means higher percentage of unsaturated fatty acid present, degree of unsaturation, lower will be the melting point. Lower will be the melting point. How can we distinguish between a fat and oil? Commonly, fats are substances which are edible triglycerides, but their melting points are such that they remain solid at room temperature. However, oils which are liquid at room temperature, now room temperature varies from one place to another. If you say it is the room temperature of London and the room temperature of Purulia district, those will be quite different. So a standard value is needed for temperature, which is 25 degrees centigrade. So we must say the substance, edible fat or oil which is liquid at 25 degrees centigrade, those are known as oils, while those which are solid at this temperature, those are fats. That is the basic difference. There is no other difference between them. And also you cannot say fats differ from oil in the sense that they contain only saturated fatty acid. No, even the animal fat like lard and tallow, their predominating fatty acids is oleic acid. Predominating fatty acid is oleic acid. That means this is 18:1. See, 18 fatty acid, 18 carbon fatty acid, only one double bond. It is delta 9 fatty acid. That means after 9 carbon there is a double bond. Oleic acid is predominating. Lard contains very high percentage, above 35%. Tallow contains almost 38%. This oleic acid. Remaining fatty acids may be saturated, any other type of fatty acid. Trans fatty acids are also there, but not necessarily, since they are fat at room temperature, they will contain only saturated fatty acid. It is the crystalline structure, everything, lot of things, the forces of attraction within the lattice, crystal lattice, those things determine the melting point of the solid fat, and that is why this melting point varies. And also the fatty acid play an important role in determining the packing of the crystal and determining the melting point of that triglyceride. So in case of vegetable oils, and fats, today in the next class we will discuss